Hello students, in this session we will discuss about double sideband suppressed carrier modulation. In the previous video we have studied about amplitude modulation, and by amplitude modulating a signal we will get a signal which contains carrier frequencies, upper sideband frequencies and lower sideband frequencies. See, in the case of an amplitude modulation systems, we can classify the system as like this. See, different types of AM systems are, first one is DSBFC system, that is double sideband full carrier system. DSBSC system, that is double sideband suppressed carrier system. SSBSC system, that means a single sideband suppressed carrier system. Next one is ISB, that is independent sideband system. Next is VSB, that is vestigial sideband system. So this is the classification of AM, that is amplitude modulation systems, and in this we are interested in these three systems, that is DSBFC, DSBSC and SSBSC. So in the ordinary AM modulation that we have studied in the previous class, that is a double sideband full carrier system. That means carrier upper sideband and lower sideband will be there. So that type of system has some disadvantages. That means when we are transmitting such type of amplitude modulated wave, power wastage will take place during transmission. That means we have to transmit the carrier upper sideband and lower sideband. So in that system, carrier signal does not contain any useful information about the modulating signal. Only the upper sideband and lower sideband contains information about the modulating signal. So by transmitting carrier signal there is no use. Actually it makes a power wastage. So it will affect the efficiency of the system. So it is a disadvantage of the double sideband full carrier system. So also the DSBFC system is a bandwidth insufficient system, and also AM wave gets affected due to noise in the case of double sideband full carrier system. See, I have made a mistake here. This is DSBFC, right? So due to these disadvantages, we will go for a next system, that is double sideband suppressed carrier system. That is, previous it was double sideband full carrier system. Now it is double sideband suppressed carrier system, that is DSBSC. So let us see what is this DSBSC. So in the DSBFC system, power wastage occur due to the carrier transmission. So we will go for the double sideband suppressed carrier. From the name itself you can see here the carrier will be suppressed. So in the full carrier system, carrier will be transmitted, but in double sideband suppressed carrier system, carrier will be suppressed. That means we are not transmitting carrier signal because it does not contain any useful information about the modulating signal. That is why it is called a DSBSC systems. So we are only transmitting the upper sideband and lower sideband of the modulated wave. And in this case, the transmission bandwidth is twice the frequency of the message signal, which is same as in the case of ordinary DSBFC systems. And in the case of DSBSC system, actually the modulated wave is obtained by multiplying the modulating signal. Modulating signal means information signal, and that will be multiplied with the carrier signal. Carrier signal is a high frequency signal, and usually this multiplication is achieved by the product modulator. So let us go to the details. Suppose let the modulated signal be EM, that is denoted by modulating signal. Actually this is the information signal, and it will be having the form EM sin omega m into t, where omega m is the angular frequency of the information signal. Sometimes modulated signal you can say it as a baseband signal or information signal. Whatever be the name, its equation will be EM sin omega m into t. And also the carrier signal, which is denoted by EZ, that will be equal to EC sin omega CT. Actually this carrier signal frequency will be higher comparing to the modulating signal, that we have studied in the first session. Okay, that means the carrier signal is frequency is higher than the modulated signal frequency, and we are modulating the carrier signal by using this information signal, so that the carrier signal amplitude will be varying in accordance with the amplitude of this modulating signal or information signal. So that is the process of modulation. So in the case of DSBSC, we are getting DSBSC signal by multiplying these two signals. So let us see. When we are multiplying carrier and message signal, the resultant DSBSC signal or this DSB-SC AM signal will be, we can represent it as DSBSC. That will be equal to EM into EC. So we can multiply EM with EC. That will be equal to EM into sin omega M into T into EC sin omega C into T. So we can multiply EM into EC into sin omega M into T into sin omega CT. So you can see this is a mathematical formula like sin A sin B. It is in the form of sin A sin B. You know that sin A sin B will be equal to 1 by 2 cos A minus B minus cos A plus B. Suppose this is, since omega C is the maximum frequency, so let it be sin A and this is sin B. So we will write the equation for DSBSC equal to EM into EC is a constant term. Instead of this, we can write the cos terms, that it will be equal to 1 by 2 into cos omega C minus omega M into T minus cos omega C plus omega M into T. So this is the equation for DSB-SC signal. In this equation, you can notice that here only difference in frequency terms and additional frequency terms is present. No carrier term is present, right? So in this case, when we are taking the product of EM and EC, we will get a double sideband suppressed carrier signal. That means here carrier signal is not present, that is omega C term, that is cos omega CT will not be present as in the case of DSBFC signal, but here only the upper sideband frequency and lower sideband frequency is present, right? So we can represent diagrammatically the generation of the DSBSC signal as actually we are giving the modulating signal or information signal or baseband signal, that is EM sin omega MT into the product modulator, and also we are giving the carrier signal which is a high frequency signal, that is EC sin omega CT to this product modulator, and this product modulator will find the product of these two signals. As a result, we will get the modulated signal or AM signal. This AM signal is called DSB-SC signal. Okay, so we will get a DSB-SC AM signals. Usually we know that in the previous case we studied that DSBFC signal, and in that case you know that the AM signal will have an equation EC sin omega CT plus MEC by 2 into cos omega C minus cos omega M into T minus MEC by 2 into cos omega C plus omega M into T. Actually this is the equation that we have studied in the first session of third module. So this term represents the carrier frequency, and this term represents the lower sideband frequency, and this term represents the upper sideband frequencies. So here when we are transmitting this term, actually it is utter wastage of power because it does not contain any information about the modulated signal, right? Because it contains only EC omega C term. There is no modulating signal term. Modulating signal term means either it should contain EM or either it should contain omega M, right? There is no such modulated signal terms in this part. So when we are transmitting this term, it will not contain any information about the modulating signal. That is why the transmission of this term is a power wastage. So we are eliminating this term in the DSB-SC systems. So we have now obtained the DSB when we are giving the modulating signal to carriers, modulated signal and carrier signal to the product modulator. We will get the DSB-SC signal, and its equation is EM EC by 2 into cos omega C minus omega M into T minus cos omega C plus omega M into T. You can see here that there is no carrier signal in this case. It contains the upper sideband and lower sideband signals. So we can say from the equation in the DSB-SC signal, the carrier signal is suppressed. So next we can draw the spectrum of DSBSC signal. We know that there will not be any carrier frequency term. That means FC will not be present there. Rather, upper sideband and lower sideband will be there. So we can draw the upper sideband like this. This is the frequency corresponding to upper sideband. Actually, its amplitude will be equal to EM EZ by 2. EM EZ by 2, and the lower sideband amplitude will be equal to EM EZ by 2. That is given here. See, EM EZ by 2. And the corresponding frequency for upper sideband is FC plus FM, and for the lower sideband is FC minus FM. Here the carrier frequency is shown dotted line. Actually, it will not be present there. The carrier frequency will not be transmitted in the case of DSB-SC signal. So that is why it is shown like a dotted line. So this term will be suppressed. That is why it is shown like dotted line. So when you are drawing the DSB-SC signal, you should draw upper sideband and lower sideband only. Okay. See, upper sideband frequency is FC plus FM and lower sideband frequency is FC minus FM. So DSB-SC spectrum contains two components, that is upper sideband and lower sideband. Also, we can graphically represent the DSB-SC signal. Suppose this is a modulating signal, which is a sine wave, and it has an equation EM sin omega m into t. Right? This is a modulating signal and its frequency is omega m. And also the carrier signal is shown like this and its frequency is higher. You can see when you are comparing, when this sine wave completes one cycle, here the carrier wave completes so many cycles. That is why I am saying that its frequency is higher. That means the number of times it appearing is higher. That is why its frequency is high. So carrier frequency is a higher frequency, and when we are modulating this carrier signal with this modulating signal, we will obtain a DSB-SC signal with the help of a product modulator. You can see that actually this DSB-SC signal will not be similar to the previous DSBFC signal or AM signal. Here there is a difference. Here the difference is that here the carrier term will be absent. That is why it has got this shape. Okay. And also here you can see that there is a phase reversal. Actually there is a phase reversal at this point. This point is similar to this point. That means whenever the modulated signal crosses the zero crossing, suppose if there is an x-axis like this, here modulated signal crosses the 0 point. At that moment there is a phase reversal in the DSB-SC signal. Similarly, next time modulated signal, when it crosses the zero crossing, that is here, there is a phase reversal occur in this DSB-SC signal. So in the case of DSB-SC signal, there is a phase reversal of the signal when the modulated signal crosses the zero crossing point. Also here it has a difference from the DSBFC signal, that in the case of DSBFC signal, the envelope of the modulated wave will give the modulated signal. Here the envelope will not give the modulated signal directly. Next we can find the power in the DSB-SC signal. Before that we have the DSBFC, that is a double sideband full carrier system, has a power that we have derived in the previous session. That is P total will be equal to carrier power into 1 plus m square by 2, where carrier power PC equal to EC square by 2R. But in the case of DSB-SC AM, you know that carrier power is not transmitted, only LSB and USB is transmitted. So total power can be represented as P dash total, which that will be equal to PLSB plus PUSB. And we know that PLSB and PUSB, that we have an equation that is m square divided by EC square by 8R. So when we are finding P dash total, we will get m square EC square by 8R into 2. That will be equal to m square EC square by 4R. Here we can separate m square by 2 and EC square by 2R, and you know that this term is PC. That means in the case of DSB-SC signal, the total power will be m square by 2 into PC. But in the case of double sideband full carrier system, the total power will be PC into 1 plus m square by 2. Right? That means the carrier power will be absent in this case. So we can find the total power saving, that is power saving will be equal to P total minus P dash total divided by P total. So when we are substituting for P total and P dash total, we will get the equation like this, and by solving the equation we will get the value as 1 by 1 plus m square by 2. These all are simple mathematical steps. You can simply substitute P total value and P dash total value, and you can cancel the similar terms, so that finally you will get 1 divided by 1 plus m square by 2. This is the power saving when we are suppressing the carrier in the case of double sideband suppressed carrier. So we can find the equation for the percentage of power saving, that will be equal to 2 by 2 plus m square into 100%, and these equations will be useful for doing problems. Okay, that's all about this topic. Thank you.